where we start? At the bottom. Can you read here? If I keep this high? That line is okay. Remember myself. I should get that one. Okay. So yesterday, we started by stating a proposition which I now want to prove. By the wheel. So which was telling that X is not projective, then M is equal to 1 and G equals to 0. Today, so remember that we had that I can write. We had a sequence where this was our finite group action. So this is but alpha was the group character, so such that representing the action of each element of the group on the symplectic form, which is again omega x. Okay? So we want to prove that if we are on a non-projective, irreducible, or non-symplectic manifold, which is our assumption, and I won't state it again, then M is equal to 1 and G acts symplectically. And the second part was proving that the Euler function of M is the value which is smaller or equal to the second number of x minus h part. Right. Okay, let's see the proof of it. Okay. Suppose that is not the case, and that M is greater than 1, sorry, strictly greater than 1. Then there exists an element in our group that is not invariant, right? As a consequence, if you look at the intersection of the h to 0 with the invariant part of the lattice, which for now I will denote like this, but in a minute it will have its own notation. This intersection is 0. Okay? All right. Now we want to use the two following facts. And the scalar cone, which is denoted like this, remember, so this is the scalar cone of x, is open inside here. And rational cohomology is dense. All right. So from this open, you deduce an open inside. An easy open inside. Let me not write it, but we just take h to 0 sum h02 intersected with h2 inside plus the current cone. Okay? And what you obtain is an open inside here. And thus by density, we get the intersection is non-zero. Okay, let's take an element in this intersection. So this is a rational class which has some component in the intersection, the real part of h to 0 plus h to 02, and then it's one component, it's scalar. Okay? All right. we take h hat to be the sum from 0 to the order of what? Of g minus 1 of course, reason I this class is invariant. I hope you agree. Okay? No, here, but in here. This is invariant, right? And we just discussed that there is no intersection with H20 and even with H02 for the countercase. It's the same, right? In other words, by these properties, in fact, a hat is of 5.1. Right? And we are done because this is clearly hyperkähler, so this is an ample class, and the variety is projective. Okay? Rational kähler.
Could H hat be 0? Could H hat be 0?
No. Let me see. No, because it's a sum of scalar classes. So each of these are each of these are the components of the scalar class. Okay? So I don't think it's anything. Okay?
I'm sorry, I didn't quite get what V is.
V is the open that you've taken. So this is not the right dimension to give an open inside the folder. Okay, let me write it explicitly. Is H20 sum intersected with
Okay.
okay? All right. Second part. The second part, we are going to prove this lemma. Suppose that we have one of these two assumptions only. So either alpha g is equal to 1. So let G be an element of our group. Okay. Suppose that either alpha G is 1 or there exists. Now I need a notation for the transcendental lattice, and considering how I denoted the tangent bundle and how we denote the invariant one, I think that's the notation I want to use. So this will be the transcendental lattice of X, right? I'll write it in a second. Just let me finish the statement on the lemma. Suppose that either alpha g is equal to 1, or there is a transcendental class which is invariant, then the restriction of G to the transcendental of X is the identity on the transcendental X, where I denote the transcendental lattice is nothing else that is orthogonal with respect to the quadratic form of the demonstrator. Okay? Okay, let's first see. Let's first prove the I hope it's enough.
There's a hole over there.
Ah, so that's so we don't do it. Otherwise, we will get lower and lower, which is not what I want. All right, proof of the lemma. So the proof basically is based on this observation, which holds for both cases. Take any element of the transcendental then if we pair, I said the bin without connection. If I pair these two classes with respect to the Bogomolov model, right? What do I get? Is an isometry. So we expect to obtain this. Okay? On the other side, on the other hand, this one is G. As a consequence, we get that alpha G minus 1 times the pairing between omega and the difference between the image of period G of C, that leads us to this image. Okay? I'm just comparing these two. Or maybe I cannot do, no, sorry, this part I have to do. You're looking at me in puzzle because it's forced. Anyway. Okay, let's start from this. This is true. The qualities we are going to use. So suppose that alpha G is 1. Okay? Now I can do what I wanted to do. I can compare. So here I have 1. I get, I forgot the name here, sorry. But this is 0. Now it is correct. Okay? This means that this class is in the orthogonal of the symplectic form, and we recall that by the property of Bogomolov model projective form, it means that this is in the Néron-Sévère. Okay? But T was in the transcendental, so I'm saying that it is in this intersection, so it's 0. This is also for any class in the transcendental, so we get the depth on the transcendental. Okay? So that's the first assumption. In the second case, consider the equality. Yes?
Sorry?
Yes.
First case, I mean, the class.
Sure. I agree. Yes. That's, I think, easier to split the two.
It's but it's well, right? It's not so obvious because, right? Because in the first case you're talking about omega x, which is not in the transcendental lattice.
I agree. It's not in the transcendental lattice, but probably from omega and omega by.
Yes, it's yeah, I mean, yes,
in there.
it is, but it's
but
not
it's
so
longer. I mean, the period won't be in the transcendental lattice, which is the integral, right? Not necessarily. Okay? Transcendental is in H2x Okay? It's true that you can probably cook a class starting from H2 but I didn't try, so let's keep this line of proof, which works. Okay? So let's go back there. So consider this equality for T, which unfortunately is still for T. I should have called it T0, but anyway. So T. So that's that. Okay, what we get is that T in our assumption, which we assume is existed, we obtain this one. Okay? So, again, now, it's true that we get this. This is 0. He was non-zero and then transcendental, so this one cannot be 0 for the same reason. For this reason, okay? So it is different from 0, hence alpha g has to be 1, hence usb. Okay?
So you don't seem to need the integrality in the part of part B.
I know, I'm using this.
Yeah, but I mean, if you look, for example, extend scalar is the complex number.
Mm-hmm.
Then that A is the special case.
Yes, okay, probably. In any case, even with two proofs, probably, we get to the conclusion of the lemma, right? As long as we agree on the statement, there is no worry. And now that we have our lemma, let's finish the proof of the proposition. So, and the proof. Okay, let's now place G0, G, one element which realizes the maximum for alpha. Okay, so that's the group span by alpha G0 is exactly M. Okay? All right. Now, lemma with assumption, so now alpha of G0 to the power M is 1. Simply because it's just by multiplicativity. Okay? So by A of our lemma, we know that G0 and power respective to the transcendental acts as the identity. Twice too much. Is it okay? Can you still read? Not too much. Okay. Now, on the other hand, take any divisor of M, D, and consider the D power. This has to be different from 1. Okay? That's just a requirement. Which tells us okay. And we know that this is not going to be the identity. on the transcendental. Because if it was, you go to the complex numbers and do the arbitrary in the period, oh, the symplectic form, sorry, I didn't mention periods yet, so, okay. And that tells us that there exists, so B holds for B0, Z. This implies that all eigenvalues of B0 are primitive and subunits.
How do you see the defaults for this unit?
Are it different from the identity?
D1 is an assumption of a fixed point. And we have not.
But I'm saying that this math is different from the identity, so that I'm sorry. I wrote exactly the opposite. G does not hold. Of course. I'm just using the negation of the statement, obviously. Okay. So, this implies that all eigenvalues are primitive about utility, which tells us that, in fact, the characteristic polynomial of our G0 is divided by the cyclotomic this is the cyclotomic polynomial of order m divides G0. Okay? Now, its degree is the Euler function yes, of m. Okay? Of course, of the restriction. And the degree of this one is just the rank of the transcendental, which is exactly the second Betti number minus 55. Okay? What's the question? No question. All right. Well, I'll start writing the numbers, and you can complete by exercise. You look at non-deformation type. We know the secondary number, and so we can give a bound on M. We take A3, we have 22 here, and this 66 was computed by Nikulin. As I said, the proposition holds in full generality by generalization of Bourville, but the original argument in complete free surfaces by Nikulin. Okay? Okay, for n is 23, but we don't gain much. Well, we gain one possible prime order, because the Euler function is not growing, right? So it increases. So a new prime order is possible, but the upper bound is the same, and so you can try compute the opposite. So while I erase, for one, perfectly fitting with the German version, and while I erase, I'll mention that you can see now that one possible direction of research is investigating maximal group actions. Okay? You can try to maximize M, and of course you have the symplectic part which can grow big. That has been done, sorry, that has been done for K3 surfaces. starting from work of type, and recently for K3 and type by Mason, and I have to say that there are very recent works by Vavak. I'm not sure if I can pronounce it right, more or less correct. Studying maximal group actions that you can have on a K3 type, and which was also later studied by comparing the data and the method. Yes. Instead, now we are going to what I will do is we will now switch to study variance of automorphisms. I wanted to give examples, but since I'm going slower than expected, I will postpone them for now. In this section, I just want to recall some invariants that are associated to automorphisms of irreducible lattice-theoretical manifolds. As you said, now I restricted to cyclic groups. Okay, somehow. Or, well, on all elements, anyways, you start from the elements of our science relation. First tool is lattice theory, which I don't want to discuss, even if I use it a lot. But here I need to mention a few things. So we've seen that for any, and let's say finite order, just to recall our assumption, we get an isometry of our lattice. That may be noted by Alan. Okay, so let me introduce some notation. There are two sublattices of L that you can associate naturally to this isometry. Okay? But we can do the notation, I mean, the notation I can give more in general for groups. Let's ignore the group and let's do it for automorphism. Okay. This invariant sublattice. Okay, there are two notations for this. My choice is T with the name of the automorphism index. So this is invariant one. And what is usually called the co-invariant lattice. Is nothing else but the orthogonal inside L of your invariant lattice. Okay. So properties. I should remember to restart here. Okay. Okay, more in general. Fg action on our manifold is known by Tg the fixed one for all elements, so the intersection. And by SG, the covariant will be the orthogonal of the line. Okay? The properties, well, first of all, they are primitive sublattices. Which means the portion out of the ring. For all elements of our lattice, the sum over the elements of the group of all the images of X is in the invariant lattice. For elements of L and for elements in the group, this difference is in the co-invariant lattice. Finally, this is the finite index extension now, if you consider the direct sum of the invariant and the co-invariant inside out. Okay, so this is the finite index group that you will obtain, and we know this is the G torsion. And I think it's an exercise, really.
In particular, TG is non-degenerate.
Yes, both.
Why is TG non-degenerate? Why it couldn't be that?
You just make the complicated by definition. You see that form cannot be designed. Otherwise, it would stay something. In contradiction with non-degeneracy value. Okay? Let me. Yes. So these are two sublattices which you can associate with your isometry, and they are a good starting point to study the action of your isometry in homology. Unfortunately, I will not, as I said, give too many details of this part, but still, it's necessary to know what it is. It's useful too. I want just to say a few properties for these sublattices. It's really distinguish between the symplectic and the non-symplectic phase. Okay, so but before that, there was the last property. I want to change the highlight it here. If G is cyclic, in fact, what I denoted here, I'll try to be consistent. It's clear that this one is the kernel, so that minus the identity, and this one is the kernel that's here of this. Okay. All right, so let me skip to some part of the properties. And let's go back to consequence of this proposition that is left over. Okay? I want to give the following proposition. Maybe A and B is confusing. So it's a big one. If alpha f is 1, so the automorphism is symplectic, okay? Then the transcendental of x is contained in the invariant lattice of x. And this is pretty much obvious. But we can deduce the signature of the two sublattices from this. This will be negative, I'm sorry, the other way around. The co-invariant will be negative definite.
So we can, are you assuming the case that G is cyclical?
Yes. Yes. I mean, even if you have a bigger group action, you consider just one element, and you are considering equivariant, and it's co-invariant. Okay? So yes. This is the symplectic action phase. Okay? Let's see what happens for the non-symplectic phase. Now you start understanding why the two theories sort of diverge. If your automorphism is non-symplectic, the invariant is contained in the Néron-Severi, and the co-invariant contains the transcendental. Moreover, the invariant is hyperbolic. We know that this is hyperbolic, okay? Because m is different from 1. So x has to be projective, and by Albrecht's projectivity criterion, we know that Néron-Severi is hyperbolic. Okay, that comes from previous statements, but now we remark that this is hyperbolic. And this is of signature to something. We know a lot more about this kind of rank invariants that you can associate, but I don't have the time to discuss them. Still, it is important, and I mean, it is important also because it tells you which kind of modular space you can take. Okay? All right. So let's give a proof. Here's one. This one allows me to clarify a point which was up yesterday when I wrote the matter from the directional group of X to the isometries. Okay. But first, so from the lemma, we are in case A of the lemma. Okay? So we know that F restricted to the transcendental X as the element. Which is this one. Okay? It tells you that transcendental is contained in the invariant part. Alright? Moreover, let alpha be a scalar class on X. This was not true when I wrote it for all automorphisms, but it's true for finite order automorphisms. Take the average, what we call the average. Okay. What you obtain is still a Kerr class, which is invariant. Okay. So if an automorphism, it preserves the Kerr code. But if it's finite order, you actually can get invariant Kerr classes. Okay? So this is Kerr, and it's invariant. That's really new business. So now we have the symplectic form is invariant, its conjugate is invariant, and we have a Kerr class which is invariant, and we know that on a Kerr class the quadratic form would be positive. So we have a three-dimensional subspace in our invariant sublattice. Okay? As a consequence, that is the orthogonal will be negative. That is, we know that all signatures are completely abnormal.
Can you explain the representation then? So this is
the quadratic form is positive over this three-dimensional space.
yes.
Okay? So you have a 3-0 space, which is contained in your sublattice. It implies that the signature, the positive signature, has to be at least free. That it can be at most free.
Yeah, okay. So it must be.
Okay?
This is an alpha unrelated to alpha, right?
Well, I mean, you need the alpha scalar and invariant. Because you need the Kerr class to know that the quadratic form.
No, it's not related to the alpha in the statement, is what I'm asking.
Ah, yeah, sorry, that was a very bad notation.
Okay,
Yeah.
sorry. That makes sense.
Whatever, another.
Sure. Sorry, I didn't think pedantic, but I figured if I was confused, there might be at least one other person.
No, that's
Okay.
absolutely
Great.
useful comment. Thank you. All right, second part. So what about non-symplectic automorphisms? All right, so let's take an element in invariant lattice and let's pair it on our symplectic. Again, F is an isometer at start, so we get this. And this is exactly as a consequence, X is orthogonal omega, because alpha F is different from 1 by assumption. So X is on our Nervous derivative. Okay. On proposition 1, so now the signature could be either 0, 1, by Albert's projectivity criterion. We know that the Nerón-Severi is hyperbolic. I just have to argue that it is 1, but we have already seen it. It was proposition 1 telling us. Okay? What did we prove? We proved that if alpha F is different from 1, there exists an invariant ample class. Okay? So proposition 1 plus irreducibility criterion gives that here is hyperbolic. And as a consequence, the invariant has signature 2. All right. So these are the very first basic properties of these sublattices. Maybe as a closing remark of this part, I'm sorry if I had to shorten it a lot, but maybe just as final remarks. You don't go that far knowing only this. Okay? Okay, you know which signature are your sublattices, but you need to know more. Namely, you need information about their discriminant. Okay? And even about their discriminant groups, if you wanted to find them. Okay? So that's probably the remark I want to do. So, and this is only if G is equal to that of time over. Then, you know the following. So, there exists an A integer such that over here. So we know that this has to be of p torsion. So the first integer is not going to surprise you too much. Let's just say that this has to be of p torsion. The existence is such that. And the other one is also not very surprising. So you have a representation. If you look at representations of your group, the invariant will take care of the one eigenvalue. Okay? All other eigenvalues, all other irreducible representations, which are non-trivial, will be in SF. Once you tend to see. Okay? And this accounts for the fact that its rank has to be a multiple of 3 minus 1. Right? And from there, you can actually, with a little of work, but now you have to fix your L. Okay, so depending on the deformation family, you can now start studying isometries of prime order P, which act on your L. So for the K3 case will be a unimodular lattice, but for all the other cases, it's 1P, and try to say which kind of pairs of T and S which can arise as invariant and co-invariant lattice of such an isometry. You need an upper bound if you want to stop, and we have one. So if you want a reference for this, and to look more into it, I think, so this was first done in many papers. You probably find good references in a paper, in one of the final papers by Hausdorff, taken, and studied. They have a more or less exact history of this result. And nowadays, this has been superseded by results by Brander and Catania, which with deeper study of the lattices obtain a way to study all isometries of prime order on any of the irreducible holomorphic symplectic manifold lattices that we know. Okay? So this is the complete tool study isometry. Okay, these are the endpoints. It was done first for K3 surfaces, of course, already by Nikulin. Then we did for K3 to type with Manuel and Alessandra, and also with Giovanni, and with Alberto for K3. And there are many more results which I'm not citing, I'm sorry, for other deformation families, but all of them, I mean, by Mongardi, Vander, Varius, a lot of L, and obtain the pair here. To my knowledge, non-prime orders are way more difficult. And there is not a full somehow picture of this action. Not yet, at least. I know that some people, even in this room, are working in non-prime order, so maybe they are the good ones to ask. Okay? So far for lattice theory, I just wanted to tell you the basics. And now let's see the other stuff. Okay, lattice theory, but once I know the invariant and the co-invariant sublattice, why I should care somehow. We want to study the geometry of our automorphism, right? So the other tool is the Sardi. There is a geometrical invariant which is clearly attached to our automorphism, which is the fixed locus. And it's geometry. It gives us the bridge between geometry and lattice theory. Okay, because we have well-known formulas, most of which work also for other manifolds and varieties, of course. But first of all, let me recall a property, which is I mean, by experience, when I give seminars, well, not so expert as you are, but in normal equation, I always get lost. So let me just remember that if you have an automorphism on a smooth projective variety X of finite order, then the fixed locus is smooth. Okay? Which means that if it is reducible, it is a disjoint union of its connected components. Okay? So that's the first property that we get. The other essential tools that we use finding the fixed locus of an automorphism may be very easy or extremely difficult, depending on the example you're looking at. We will see examples in the next lectures. So if you have a Fano variety of lines, or you have an Hilbert scheme, you can easily compute the fixed locus. If you are on a modular space of sheaves, your life becomes much harder. Okay? There are very recent works trying to attempt that computation. Essential tools to relate geometry of the fixed locus and lattice theory, let's say. The bridge is given by two things. I wanted to recall more in detail, but here also I will need this with so we have Lefschetz formulas, which we will study. or Smith theory. This uses the equivalent cohomology applied to the action of your group. It stands for irreducible holomorphic symplectic manifolds in a paper by Hausdorff. I want to give any detail of the formula, but it's here. But Lefschetz formula, let me just recall because I will use it as an example in a second, the topological one. So, we have that if you do the sum from I to twice the dimension of your x, the alternative sum of the traces of your action in commodity, what you obtain is Euler characteristic, a topological Euler characteristic of the fixed law. Let me say that this is not enough usually, but sometimes it's not enough. Again, here it's in my experience, it's usually enough for non-symplectic, because anyways you need to go heavier on lattice theory, and so get through mixed theory. For symplectic ones, you usually also need holomorphic Lefschetz formulas. Okay? These are holomorphic Lefschetz formulas. I won't write on the blackboard now because otherwise I'll finish my lecture with that. Okay, let's see an example to finish. Okay, or what I'm saying. This is the second part of the course. I will focus on symplectic actions. Now let's give an symplectic example. Okay. All right. So let's take y contains amplifier as most cubic orbifold, but not any. We are going to take y, which is the triple cover of C4 branched over a most cubic squiggle. This is one of my favorite examples. Okay? So you get an induced cover map over the free on your cubic squiggle. If you want, the equation of y will be, let's say, x5 to the cube equals this one. Okay? All right. You got an induced. Maybe I call it still sigma, or do you want it tilde? Is anyone bothered for me keeping the same name for the map? No. Okay. We get an induced automorphism on the panoramic lines, which we have said is the fourfold of K2 time. Okay? Forward. Okay. As I said, in good cases, that is panoramic line, it's easy to find, really compute the pixel logs. So while I erase, you may compute it for me. On the panel, of course. Sorry, I finished. Probably I shouldn't have worked the second one. It got you scared. It was just going. All right. So what's the pixel locus? So these are invariant lines. Okay? Either they are lines of fixed points, or they are lines for two fixed points. You see that there are no lines of fixed points, I think, but in any case, this is the Fano surface of lines contained in your figure. Okay, so these are lines. This is a classically studied object related to the surface for peoples. You know everything, so let me tell you the magic number. So, in particular, its general type is 3 equals 27. All right. Now, I can plug it into my lecture formula, and I get this is equal to 2. There is not much where what is the phase times 0 in this case. Then we have twice the phase of our sigma restricted to the H2 over Fy R and the phase of the action of sigma on the H4. This is easy to obtain from what we said. The action on H2, well, it's easy. We can relate it to in some of our invariants in lattice theory, right? It's the rank of TF minus M. I think it's clear that it acts with the plus one part. With this one, then each of the other two eigenspaces as I mentioned M, we are going to our nuclear phrase. Okay? As I said here, I start from a geometrical example. So the geometry comes out. Now I want to understand in which case I am. So what's the invariant lattice? What's the co-invariant? Okay? Maybe I'll finish off next time so that I don't steal too much time to this year. Try to compute, just to finish off the example. So to compute the trace on the H4, you just need to remember that for K3 to type, you actually have the H4 is the sim2 for H2. Okay? So once you know the action here, you can deduce the action on H4 and the compute the trace. That's a little bit big. And also try to show that sigma is not symplectic. And now I'm really done. Thank you.